Hello everyone, and welcome to today's chem lesson. Today we are going to introduce the idea of a potential energy diagram, which tracks the energy of a reaction as it goes from start to finish. Before we can really dive into that though, let's take a look and see if we can correctly fill in the blanks for these. Right, I have 4 word choices here. I need you to take a look at these sentences and pick which word should correctly fill in each blank. We've talked about endothermic and exothermic things before, but the idea of the second sentence for each pair, right, the products having higher or lower potential energy, that's new. You need to think and apply what you know in order to get that answer there. So take a couple seconds, take 30 seconds, and see if you can correctly assign the right word. The correct way to fill in these blanks looks a little something like this. Endothermic reactions are reactions that take in energy. We talked about that way back in Unit 2 when we looked at our heating and cooling curves. Endothermic is when energy enters. So they take in, they absorb energy. This means that the products, the things that we make, the things on the right side of the arrow, are going to have higher potential energy than the reactants, right? We're absorbing energy, we're storing energy. On the flip side, an exothermic reaction is a reaction that releases energy, right? Exothermic energy exits. So they're releasing energy. And if that's the case, then the products, the things that we create, are going to have lower or less potential energy than the things that we started with, right? They have released energy, and so their products have lower potential energy. The idea of a potential energy diagram is the idea of taking these two sentences and putting them into a picture form. And that's going to look a little something like this. An exothermic potential energy diagram shows energy being released. Products have less potential energy than reactants. An endothermic reaction shows products absorbing energy, right? Or reactants start low, we absorb energy, and we end with more energy than we started with. There are only ever 2 shapes for a potential energy diagram. It either looks like the endothermic one over here on the right, or it looks like the exothermic one over here on the left. And what we're tracking, like I said, is potential energy, right? This is potential energy. And we are tracking it over the reaction pathway, which is just time. As our reaction goes from start to finish, we are tracking how much energy there is. Right. There are other labels, right? Activation energy and delta H, which we're going to talk about in a second. Right, but let's take just one more slow look at exo and endothermic shapes. We start here, right, on the left side, and these are the reactants. They have some amount of potential energy, right? Notice there's no numbers here. The reaction begins and then ends with the products, right? And the products, in this case, because it's exothermic, have less potential energy. We have released energy. All of the energy in the middle is gone. We have put it out into the environment. For an endothermic reaction, we start with our reactants. Our reaction happens, And when we get to our products, we have more energy than when we started. We have taken in energy from the surroundings and stored it as products, right? As chemical bonds in our products. Now let's look at these two other labels that we have here. Let's put one in purple. Gotta love purple. We've got activation energy, and we've got delta H. We're going to talk about each one in more detail before this video is over, but let's put some groundwork for them first. Activation energy is the amount of energy needed to start the reaction. Right? The amount of energy needed to start the reaction. Sometimes that's a large amount of energy. Sometimes that's a very small amount of energy. Sometimes it's something in between. Every reaction has an activation energy. Every reaction needs some amount of energy to start. Whether it's exothermic or endothermic, either one needs some energy to be put in order to start this process. And you know this is true too. If you take a match out of the box and you just hold it and stare at it, nothing happens. Even though the burning of a match is an exothermic process and it releases a lot of energy, it won't just happen on its own. There's not enough energy in the room to start that reaction. You need to strike a match across the side of the matchbox or generate enough friction to start that reaction happening. An endothermic reaction we also know is true. You go to bake a cake. You mix all your ingredients together and you take your cake batter and you stick it on the countertop. And you say, "Great, I've made a cake." And you walk away and you come back the next day and you do not have a cake sitting there. Right? You have not put in enough energy for that reaction to happen, for the chemical reaction to happen and bake your cake. You did not put that cake in the oven, where it will take all of the energy that the oven gives it and become a cake. Right? So it doesn't matter if it's an exothermic match or an endothermic cake. Every reaction needs energy to be put in order to start. All right, let's look at activation energy in terms of the overall process. Right? Because I hear you and you're saying, "Mr. M, but an exothermic reaction releases energy. Why does it need energy to start?" Right? Look at how much energy is needed to start the reaction. We need to put in this much energy, right? From the reactants to the top of the bump. Right? That's the energy we are putting in. And then look at how much energy we are getting out, right? The downward slope of the hill here is releasing. What do we do more of for an exothermic reaction? Do we absorb more or do we release more? Look, we're releasing more energy than we are absorbing. Right? We absorb a small amount, we release a large amount. Exothermic releases energy. An endothermic reaction, the activation energy is from the reactants to the top of the bump. This is how much energy we need to absorb in order to start this reaction. And look at how much energy gets released. right? Where we push all the way up the hill, and as we go down the hill, that's the release of energy. An endothermic reaction absorbs more than it releases. Endothermic reaction is all about taking in energy. Right, so that's activation energy. The last thing we're going to mention with activation energy is a catalyst. Right, we talked about a catalyst in our previous video, right? We said that those help speed up reactions because they lower activation energy. If I were to add a catalyst to this exothermic reaction, the thing that changes is the height of the bump. Instead of having to go all the way up here, now the reaction only has to go down to here. Right? We have to absorb less energy in order to start the reaction. Right? It could be more drastic, right? We can say that's the new bump, right? It has been lowered to here, right? Significantly less activation energy needed. And it works for endo and exothermic things. Ooh, that's not a good line. Let's try again and pretend like I know how to draw a line. Fine, right? Good enough. I have lowered the activation energy, right? This is the new activation energy, is only up until this point. Right? I've cut out all of that energy that needs to be put in. Right? And if you have less energy that needs to be put in, then you have a reaction that starts faster. Now we've got delta H. Delta H is sitting here, it's hanging out. And we're going to talk more about delta H as we keep going as well. All right, delta H is the difference in energy between the reactants and the product. It's the change, because remember, delta always means change. Change in potential energy. All right, and it just measures the difference between the reactants and the products. Right? From your start to your finish, how much energy have you gone up or down? Exothermic reactions go down in energy. They release energy. They give you a negative delta H. Endothermic reactions go up in energy. They absorb energy. They give you a positive delta H. The change is positive. You have absorbed and gained energy in an endothermic reaction. Change is negative for an exothermic thing. You have released energy. You have less energy. You have gone down in potential energy. Let's talk more about activation energy. I've got a little example to show us, right? Like I said, activation energy is the smallest amount of energy needed to start a reaction. Everything needs some activation energy. Sometimes it's high, sometimes it's low. But everything needs that initial little kick to get it going. Everything needs that activation energy to start it. And like I said again, catalysts lower activation energy, allowing the reaction to start sooner than it usually would, which increases the speed at which the reaction happens. If we look at this video, which I can't start while I am in pen mode, we get to watch this happen, right? This aspect right here, as we are adding the activation energy, we are striking the match. And as soon as here, right? As soon as the match comes off, we have added enough activation energy and we can have that reaction keep going on its own. All right, let's do a little potential energy diagram. For an exothermic reaction, it's going to look like this: start high, end low. Let's restart. Right. As the match is being struck, this entire portion is adding activation energy. All of this until here, exactly here, where the match comes off. That will now continue to burn and burn and burn until we reach our products. Right? The adding of the activation energy, the striking of this match, this entire portion of time in slow-mo is the adding of the activation energy. Once the match comes off the strike pad, that reaction has been given enough energy to keep going, and it will burn, 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 burn until it reaches the bottom of this hill and becomes ashes. Let's do a little bit of a check-in here. We're going to draw 4 different potential energy diagrams. 2 endothermic reactions and 2 exothermic reactions. 1 endothermic with a high activation energy, 1 endothermic with a low, 1 exothermic with a high activation energy, 1 exothermic with a low. Right, so what I want us to do is fill in these 4 diagrams. I'm going to give you about 45 seconds, or actually better yet, pause the video here, try to draw these out, and when we resume, right, I'm going to wait about 10 seconds of a video time, and then we're going to go over these. All right, pause the video, see what you can do. So, let's look at our endothermic reactions first. An endothermic reaction, we know, is going to absorb energy. So we're going to actually start with pretty low reactants for both of these. Right? We're going to start pretty low. We're going to end fairly high. We're going to end higher than we started. All right. These are the endothermic shapes. Now we need to put in the activation energy. A low activation energy means that this bump is going to be pretty small. So we're going to come up and back in. All right, this activation energy is going to be smaller than this activation energy. We're just going to go much higher. That's our activation energy. Right? Smaller activation energy versus higher activation energy is relative. If we're not putting numbers on here, if we're not actually putting numbers on here, activation energy is relative. As long as this one is higher than this one is low and this one is high. The 2 exothermic reactions are going to start with higher energies for their reactants and end with low energies for their products because we are releasing energy. A high activation energy, just like before, means we're going to have a big bump and go down. Alright, this is going to be our activation energy. And a low activation energy means we're going to have a little bump and then go down. Alright, this is our activation energy. Again, it's relative. As long as this one is higher than this one, we have correctly filled in these things. Both of our exothermic reactions have lower activation energies than this endothermic reaction. Right? The size of this arrow compared to the size of this arrow, compared to the size of this arrow, compared to the size of this arrow. Alright, this is the smallest. And this is the biggest. Right, depending on where you put your reactants and products, some of these arrows might be a little different, right? But as long as these are the shapes, right? Starting high, ending low, starting high, ending low. Those are exothermic. Starting low, ending high, starting low, ending high. Those are endothermics. And like I said, activation energies are relative. As long as the low is smaller than the high, you are looking good. Now, before we're done, we're going to talk a little bit more about delta H. Delta H, like we said, is the heat of reaction. It's the change of potential energies. And if we look, right, it's the comparison between the reactants and the products. How much did we grow, or how much did we shrink? How much did we gain, or how much did we lose? And like we said before, right, delta H, if it's positive, it means you have absorbed energy, you've gained energy, you've gone up in potential energy. If delta H is negative, energy is released, you have lost energy. And we get delta H by comparing the products, sorry, let's go back to green here. The products minus the reactants. So this starts high, ends low. That's exothermic. If we put numbers here, let's put a 3 and an 8, just arbitrary numbers. If I wanted to take the delta H for this reaction, it would be 3 because that's what my products are, minus 8 because that's where my reactants are, giving me a negative 5 delta H. And like I said, negative is exothermic. Alright, let's roll it back just for 1 second and look at the delta H's of each of these reactions here. Let's put in some numbers and look at the delta H for each of these 4 things. Alright, delta H is always products minus reactants. Let's draw nice and even. Look at that beautiful straight line. Look at me go. So good at drawing straight lines. Alright, let's put some numbers in. We're going to call this a 2. We're going to call this a 5. We're going to call this a 5. We're going to call this a 3. These are 1s and 6 and 7. Take a second and see if you can calculate the delta H for each of these reactions. All right, remember, delta H is products minus reactants. If we're looking, let's go counterclockwise. Here, products minus reactants is 5 minus 3, giving us a delta H of positive 2. Here, delta H is products minus reactants, which is 5 minus 2, giving us a delta H of positive 3. here, delta H is product minus reactants, which is 1 minus 7, giving us a delta H of negative 6. Here, delta H is products minus reactants, 1 minus 6, giving us a delta H of negative 5. And what kind of connection can we make? We can say endothermic. Both of these are positive values. We have gone up in energy. We have absorbed energy. Here we can say exothermic. Those are both negative. We have gone down in total energy. We have released energy. And so, if we look back now at our notes, a positive delta H is an endothermic reaction. A negative delta H is an exothermic reaction. This does match exactly what we just drew. It matches what we've been looking at throughout this whole video with the shape of these potential energy diagrams. We're going to take another look at delta H in our next video when we look at the reference table. We're going to look at reference table I, and we're going to talk about how that helps us look at delta H's and compare delta H's and what we can do with the information that's given to us there. But for now, I'm going to say we're done with this video, and I want everyone to have a fantastic day.